Ever wondered how a massive airplane, carrying hundreds of passengers and tons of cargo, manages to soar through the sky? It's a question that has sparked curiosity in many minds. It's not magic, but the marvel of flight, bound by the laws of physics and principles of engineering. This journey we're embarking on aims to unravel the mystery that makes this extraordinary feat possible. We'll delve into the intricacies of how airplanes defy gravity, especially when burdened with hefty loads. From the fundamental forces at play to the significance of wing design, from the role of mighty engines to the crucial aspects of control surfaces, and from the delicate balance of weight distribution to the safety measures in place, we will explore it all. The magic of flight is a complex interplay of aerodynamics, engineering, and design. It's a testament to human ingenuity and the relentless pursuit of innovation. So buckle up as we take off into the fascinating world of flight. To understand how airplanes fly, we first need to grasp four fundamental forces: lift, weight, thrust, and drag. In the world of flight, these forces are like the four cardinal points on a compass, each playing its own crucial role. Let's start with lift. Lift is the upward force that defies gravity, allowing an airplane to rise into the sky. It's generated by the airplane's wings, which are shaped in such a way that air flows faster over the top than the bottom. This difference in speed creates a pressure imbalance, with lower pressure above and higher pressure below. This imbalance is what propels the airplane upwards, a concept known as Bernoulli's principle. Now, opposing lift is weight, the force of gravity pulling the airplane down towards the earth. The heavier the airplane, the more lift is needed to overcome this gravitational pull. That's why larger planes need bigger wings, more powerful engines, or both. Next, we have thrust, which propels the airplane forward. It's produced by the engines, which suck in air, compress it, mix it with fuel, and ignite it. The resulting explosion pushes hot air out the back, propelling the plane forward. This is essentially Newton's third law of motion in action. For every action, there's an equal and opposite reaction. Finally, acting against thrust is drag, which is the air resistance an airplane faces as it moves through the sky. There are two types of drag: parasitic and induced. Parasitic drag is the resistance from the air as the plane moves forward, while induced drag is created by the same action that produces lift. In a well-designed airplane, these forces reach a state of equilibrium, allowing the plane to maintain steady flight. When the pilot wants to change the plane's flight path, they manipulate these forces by adjusting the throttle, altering the wing flaps, or changing the plane's pitch or yaw. These forces are the invisible hands that guide an airplane in flight. They are the foundational principles that allow us to conquer the skies. The wings of an airplane are critical for flight, but why is their shape so important? Well, let's delve into that. The shape and design of an airplane's wings are key to generating lift, the force that counteracts gravity and keeps the airplane soaring in the sky. The curved top and flat bottom of a standard airplane wing design, known as an airfoil, are no accident. This shape takes advantage of Bernoulli's principle, where air flowing over the curved top of the wing moves faster than the air flowing beneath, creating a pressure difference and, in turn, lift. However, not all wings are created equal. The design of the wings can vary greatly depending on the intended use of the aircraft. For example, long and slender wings, known as high aspect ratio wings, are common on gliders and large commercial airplanes. These wings minimize drag and allow for efficient, long-duration flights. On the other hand, shorter and broader wings, or low aspect ratio wings, are seen on fighter jets and sport aircraft. These wings provide greater maneuverability at high speeds, but are less efficient at cruising speeds. Then, we have the swept-back wings, instantly recognizable on many modern jet aircraft. The angle of these wings reduces drag at high speeds, making them ideal for fast, long-distance travel. But how about those wings that seem to move? Well, those are variable sweep wings seen on some military aircraft. These wings can change their sweep angle mid-flight, offering the best of both worlds: high speed and maneuverability when swept back, and efficient, slower flight when spread out. And let's not forget the intriguing forward-swept wings, a rare sight indeed. These wings, like those on the experimental X-29, can provide excellent maneuverability and efficiency, but they also come with their own set of stability challenges. The wings, therefore, are more than just appendages. They are the heart of an airplane's ability to fly. Engines are the powerhouses that push an airplane forward, but how exactly do they work? Airplane engines work on the fundamental principle of action and reaction, straight from the pages of Newton's third law. When the engine expels air or exhaust gases backward, it creates a force in the opposite direction that propels the airplane forward. This force is what we call thrust. Thrust is the muscle that overcomes drag, the resistive force that tries to slow an airplane down. It's like a tug-of-war between thrust and drag. When thrust is greater, the airplane moves forward. When drag takes over, the airplane slows down. It's a delicate balancing act that keeps an airplane cruising at a steady speed. But not all airplane engines are the same. There are two main types of engines that you'll commonly find in commercial aircraft: jet engines and piston engines. Jet engines, as the name suggests, generate thrust by jetting out a high-speed stream of exhaust gases. These engines operate on the principle of jet propulsion, which involves sucking in air, compressing it, mixing it with fuel, and igniting the mixture to generate a powerful jet of exhaust gases. Jet engines are known for their power and speed, making them a popular choice for commercial and military aircraft. On the other hand, piston engines are more like the engines in your car. They use a series of pistons to compress air and fuel in a combustion chamber. The mixture is then ignited, and the explosion pushes the pistons down, turning the crankshaft. This motion is then transferred to the propeller, creating the thrust needed for flight. Piston engines are typically found in smaller aircraft due to their simplicity and reliability. So, whether it's the roaring jet engine of a Boeing 747 or the humming piston engine of a Cessna, engines play a fundamental role in flight. They provide the thrust that overcomes drag, propelling the aircraft through the skies. Without these powerful engines, an airplane would simply be an immobile structure. An airplane in flight needs to move up, down, and sideways, but how is this control achieved? Well, let's dive into the world of ailerons, elevators, and rudders, the control surfaces of an aircraft. The ailerons, found on the trailing edge of the wing, control the roll of the airplane. When the pilot moves the control stick left or right, one aileron lifts while the other drops, causing the airplane to roll. Next, we have the elevators, located on the tail. These control the pitch of the airplane. When the pilot pulls back on the control stick, the elevators rise, causing the airplane's nose to lift. Pushing forward on the stick has the opposite effect. Lastly, the rudder, found on the vertical tail fin, controls the yaw or side-to-side movement. When the pilot presses the pedals, the rudder swings left or right, causing the airplane to turn. These control surfaces are the steering mechanisms that pilots use to direct the course of an airplane. An airplane carries a lot of weight, but how does it maintain balance? Well, the answer lies in the careful management of weight distribution. Just as a tightrope walker uses a pole to balance their weight, airplanes distribute their payload evenly across the aircraft to maintain a stable center of gravity. This concept goes beyond just stowing luggage evenly. Factors like the positioning of passengers, fuel, and even the placement of the wings and engines all contribute to an airplane's balance. This balance, or the center of gravity, is crucial to the aircraft's performance. It impacts the airplane's stability, fuel efficiency, and overall safety. If the weight is too forward, it can make the airplane nose-heavy, making it harder to climb. If it's too far back, it can make the plane tail-heavy, making it difficult to descend. Therefore, before every flight, careful calculations are made to ensure the weight is distributed correctly. Proper weight distribution and balance, therefore, are crucial for a smooth and safe flight. Some airplanes are truly gigantic, carrying enormous loads. But how do they manage? Let's delve into the remarkable world of these sky behemoths. Take the Antonov An-225 Maria, for instance. As the heaviest aircraft ever built, it can carry a staggering weight of up to 640 tons. That's roughly equivalent to 120 elephants. It achieves this feat through a combination of powerful engines, a massive wingspan, and clever weight distribution. Or consider the Airbus A380, the largest passenger airliner in the world. It's designed to comfortably transport over 800 passengers across vast distances. It's a marvel of modern engineering that it can lift such weight off the ground and cruise at high altitudes. These examples show us that size and weight, although challenging, are not insurmountable obstacles in aviation. With the right design, engineering, and understanding of aerodynamics, the sky truly is the limit. These giants of the sky are feats of engineering, defying gravity with their massive loads. Safety is paramount in aviation, so what measures are taken to ensure safe flight? Well, it's a blend of design, technology, and rigorous procedures. Airplanes are meticulously engineered with multiple redundancies. That means if one system fails, another steps in to keep the plane aloft. For instance, commercial jets are typically equipped with 2 or more engines. Even if one engine fails, the airplane can still fly safely on the remaining ones. When it comes to heavy cargo, special precautions are taken. The cargo is carefully distributed and secured to maintain the plane's balance and prevent shifts during flight. Additionally, cargo planes often have reinforced structures to handle the extra weight. Moreover, rigorous pre-flight checks are conducted to ensure that all systems are functioning optimally. And let's not forget the highly trained pilots and crew who are prepared to handle a wide range of scenarios. The safety of passengers and cargo is always at the forefront of aviation design and operations. We've covered a lot of ground, so let's recap. We've seen how the four fundamental forces of flight: lift, drag, thrust, and weight interact to keep an airplane aloft. We've delved into the importance of wing design and how the shape of a wing, with the help of Bernoulli's principle, generates the crucial lift. We've looked into the engines, the powerhouses providing the thrust to overcome drag. We've touched upon the essential control surfaces, the ailerons, elevators, and rudders, that steer the aircraft. We've also discussed how weight distribution and balance play a vital role in maintaining a safe and efficient flight. And we've marveled at the giants of the sky, illustrating how these principles apply to even the heaviest of aircraft. It's a symphony of aerodynamics, engineering, and design, all working together to make flight possible. So next time you see an airplane in the sky, you'll appreciate the magic of flight a little more. We've just scratched the surface of the fascinating world of aviation. The magic of flight, once a dream, is now a complex blend of science, engineering, and design that we've begun to understand. The fundamentals of aerodynamics, the intricacies of wing design, the power of engines, the precision of control surfaces, and the balancing act of weight distribution. All these elements come together in a symphony of physics to lift massive machines into the sky. Yet, there is so much more to discover. As you delve deeper, you'll encounter more intricate concepts, groundbreaking technologies, and awe-inspiring feats of engineering. We invite you to question, to ponder, and to satisfy your curiosity. The vast world of aviation is at your fingertips, filled with resources and knowledge waiting to be explored. Keep exploring, keep learning, and remember, the sky is not the limit. It's just the beginning. If you enjoyed this journey through the world aviation, don't forget to like, subscribe, and share our videos. Keep watching for more fascinating insights.